So let's look at an example. We will classify the conic E with equation x squared plus y squared minus 2x minus 4y plus 5 is equal to 0. So first we'll determine whether or not this conic is degenerate. So we'll look at the matrix M. Our A term is 1, our B term is 0, so half of 0 is 0. Our F term is -2, half of -2 is -1. Our C term is 1. Our G term is -4, half of -4 is -2. And our H term is 5. So if we take the determinant of M, we can expand about the first row. And so we have the determinant of the matrix 1, -2, -2, 5, minus the determinant of the matrix 0, 1, -1, -2. So we have 5 minus 4 minus 0 minus a -1, so that's 0 plus 1. And so that is 1 minus 1, which is 0. And so this conic E is degenerate. So now we need to determine what type of conic it is. So we will look at the submatrix A, which is 1, 0, 0, 1. The determinant of A is 1 minus 0, which is 1, which is positive. This implies or predicts an ellipse. So E is a degenerate ellipse, that is, it is a single point. And if we look at the equation, it has the form of a circle. So if we try to find the center, we take -1/2 of the F term, so that's -1/2 of -2, which is 1, and -1/2 of the G term, which is -1/2 of -4, which is 2, and the square of the radius would be 1/4 of the square of the F term, so that's 1/4 of 4, which is 1, plus 1/4 of the square of the G term, so that's 1/4 of 16, which is 4, minus H, and our H is 5, so that's 0. So this has this conic E has the equation x minus 1 squared plus y minus 2 squared is equal to 0. Again, E is a degenerate conic or a degenerate ellipse. That is the single point 1, 2. Now this equation can be factored into linear terms in the field of complex numbers. And if we do that, we have the factor x minus 1 plus I times y minus 2 times the factor x minus 1 minus negative I, or minus I rather, times y minus 2. Okay, so let's look at another example. So we previously classified the conic E with equation 3x squared minus 10xy plus 3y squared plus 14x minus 2y plus 3 is equal to 0. We classified that as a hyperbola. since the determinant of the matrix A, which is 3, -5, -5, 3, is 9 minus 25 is negative, and that implied or predicted a hyperbola. So let's now confirm that this hyperbola is not degenerate. So the matrix M contains as a submatrix the matrix A. And so now to complete the first row, 1/2 of the F term is plus 7. Half of 14 is 7. And 1/2 of the G term is -1. And the constant H is 3. So the determinant of M, we will calculate that using expanding about the first row. So we have 3 times the determinant 3, determinant of the matrix 3, -1, -1, 3, minus a -5, so that's plus 5, times the determinant of the matrix -5, -1, 7, 3, plus 7 times the determinant of the matrix -5, 3, 7, -1. So this is 3 times 9 minus 1, which is 8, plus 5 times -15 minus a -7, so that's -15 plus 7, which is -8, plus 7 times 5 minus 21, which is -16. So notice we have a factor of 8 in each of these. So let's factor out 8. And we have 3 minus 5 minus 2 times 7, or minus 14, which is 8 times -16, which is -128. But the important property is that the determinant of M is not 0. And so the hyperbola is not degenerate. So we now have 2 matrices that can predict the type of conic that we have and whether or not it's degenerate based on the determinant of those matrices. But we still need to be able to apply a transformation in order to answer questions about certain points, such as the center, foci, and vertices. So in choosing the vectors, the eigenvectors, for the matrix P, it is to our advantage to choose orthonormal vectors, since in that case we have that the inverse of the matrix P is the same as its transpose. So recall that the, one form, matrix form of the equation for a conic, is the transpose of the vector x times the matrix A times the vector x, plus the transpose of the vector j times the vector x, plus the constant h is equal to 0. So if we apply the transformation x is equal to p times x prime, we have p times x prime transpose times a times p times x prime, plus j transpose times p times x prime, plus h is equal to 0. Now the transpose of a product is the product of the transposes in reverse order. So we have x prime transpose times p transpose times a times p times x prime, plus j transpose times p times x prime plus h is equal to 0. Now, again, if we choose orthonormal vectors, then P transpose is the same as the inverse. And so we have x prime transpose times P inverse times A times P times x prime plus J transpose times P times x prime plus H is equal to 0, where P inverse times A times P is the diagonal matrix D. And so we have x prime transpose times the diagonal matrix D times x prime plus J transpose times P times x prime plus H is equal to 0. And so we have the advantage of eliminating the cross products and taking also advantage of the matrix D being a diagonal matrix with the eigenvalues on the diagonal to transform the coordinate system for an original equation for a conic. So let's look at an example. So again, consider the hyperbola E with equation 3x squared minus 10xy plus 3y squared plus 14x minus 2y plus 3 is equal to 0. The matrix A is the matrix 3, -5, -5, 3. And so A minus lambda I is the matrix 3 minus lambda, -5, -5, 3 minus lambda. So to find the eigenvalues of the matrix A, we set the characteristic equation equal to 0. That is, we set the determinant of A minus lambda I equal to 0. The determinant of A minus lambda I is 3 minus lambda times 3 minus lambda, or 3 minus lambda squared, minus -5 times -5, which is 25. And so we have 9 minus 6 lambda plus lambda squared minus 25. This is the same as lambda squared minus 6 lambda minus 16, which we can factor as lambda minus 8 times lambda plus 2. So the eigenvalues of the matrix A are lambda is equal to 8 and lambda is equal to -2. So we'll first find the eigenvectors associated with the eigenvalue 8. So for the eigenvalue of 8, we have the equation 3 minus 8, or -5 times x, minus 5y is equal to 0. That equation comes from the first row of the matrix A minus lambda I. And for the second equation, we have -5x plus 3 minus 8, or -5y, is equal to 0. Notice this is exactly the same equation, which we can write as 5x plus 5y is equal to 0. So we have x is equal to -y. And so the eigenvectors associated with the eigenvalue, lambda equal 8, are the vectors, set of vectors of the form c, -c, where c is any real number. And for example, a simple matrix in this set is the matrix, a simple vector in this set is the vector 1, -1. So now let's look at the eigenvectors for the eigenvalue -2. So we have 3 minus a negative 2, which is 5x minus 5y is equal to 0. And we have negative 5x plus 3 minus a negative 2, or plus 5y is equal to 0. Again, we have the same equation, which in this case is 5x minus 5y is equal to 0, or x is equal to y. So the eigenvectors associated with the eigenvalue negative 2 are all vectors of the form CC, where C is any real number. And for example, a simple vector from this set is the vector 1, 1. So notice the dot product of the vector 1, negative 1 with the vector 1, 1 is 1 plus negative 1, or 0. And so these vectors are already orthogonal. So now let's make them orthonormal by normalizing each vector. Notice that each of these vectors have the same norm, the square root of 1 plus 1, or the square root of 2. And so we divide each component in the vectors by the square root of 2, and then rationalize that. And so we have orthonormal vectors, square root of 2 over 2 minus the square root over 2, square root of 2 over 2, and the square root of 2 over 2, square root of 2 over 2 for the second vector. So we choose P to be the matrix with these vectors. So the first column, or the first vector, is square root of 2 over 2 negative square root of 2 over 2. And the second column is square root of 2 over 2 square root of 2 over 2. And so with this choice, our first vector corresponds to the eigenvalue 8, and our second vector corresponds to the eigenvalue negative 2. And so our diagonal matrix is the matrix 8, 0, 0, negative